everyone, I'm Giuseppe Maggiore and welcome to the course Introduction to C#. In this lecture, we're going to talk about custom types, how to extend the type system of C# in order to contain data structures that are only relevant for our specific program domain. We're going to start with, let's say, the easy custom types that the latest incarnations of C# have started offering in line with the tradition of functional programming. In particular, we will study reference tuples and value tuples. There are two ways of doing tuples in C# and we will look at both of them. The difference is how they are stored in memory. We will look at tuples with named fields, which are sort of half records. Then we will look at records and how to initialize, decompose, and deep copy custom records. We will talk then about custom classes and custom structs, where we have full freedom to define all sorts of data structures that we might want to. So tuples and records are sort of the fast food of data structures, if you want, but they are very, very powerful and useful. But in some sense, they are limited and very straightforward, whereas custom classes and custom structs, that's where the real magic happens, where you get full control over how you build data structures. Then we will discuss the memory layout of classes and structs and the implications of this memory model. So how is it stored in memory and what does it mean for performance, for copying, etc. We will then define and implement interfaces. So the first step into polymorphism. So using multiple different data structures that have something in common in different contexts. We will look at how we can find out which class implements the interface with a switch if statement and perform complex pattern matches with this statement. Now, obviously, arrays and primitive types could be used for building anything you want. Like you could build whatever you want with arrays of primitive types or nested arrays or this kind of thing. But of course, we want to be able to express complex concepts. And one of the things that we care the most about as developers is being able to give the right names to the right entities so that they reflect the domain that we are modeling. So, for example, you could have name 1 and name 1 and surname 1, John Doe, and then you say, no, but I have two people I want to be able to model, so name 2 and surname 2, Jane Doe. Let me start the compiler. There we go. Okay, so you might write code like this, but there is no reason whatsoever to do this because the link between name and surname 1 and 2 is only a number, and that's not really strong. That's actually quite unclear. So one of the things we want to do with custom types is we want to be able to group multiple variables together in order to, for example, denote a person. So we could say that John is tuple.create John Doe. Now, tuple.create is a generic method. We will talk extensively about generics, meaning that, oh, let's see what it's complaining about. Oh, of course. Well, we could say that the tuple that is returned is a tuple with a string and a string. So this is a generic type, meaning that the tuple is always the same definition, but the arguments that are passed to the tuple can be different, and this actually changes the type. We will talk extensively about this in the last lecture. But we can simply say var and the type will be correctly inferred to be system tuple of t1, t2, where t1 is a string and t2 is a string. And if you mouse hover on top of John, you actually don't get the type structure, but rather you get the instantiated type, which is tuple of string. Okay, notice that there's a question mark because this kind of tuple might be null. So you must always check to make sure that the tuple is actually instantiated. In this case it is, obviously, but it might not be. We could even be more precise, and if we say, okay, it's a tuple and it has two arguments, string and string, and we say this at the type level with these angle brackets, then the system expects two tuples. Interesting to notice that if you don't specify the arguments, well, first of all, C# doesn't know how many arguments there are. So in this case, I can pick the second version. And it doesn't know the types. It's saying t1 and t2. But when we pass a string, then it knows, okay, the first one is a string. And when I pass the second, let's say that the second is a date. And there you go. Now, the type of John is a tuple of a string and the date, presumably the date of birth. Now we can also instantiate Jane. We can say Jane Doe, and Jane Doe is, I don't know, a little bit older. Okay. Now all of a sudden this program looks rather different than the program where we had name and surname. Well, of course it's different because along the way the types also changed, but instead of having now the full name and the birthday, and you would call them first full name 1 and birthday 1, full name 2, birthday 2, which again will be quite ugly. Now we have John and Jane, and John contains multiple values. It has item 1, okay, admittedly, item 1 is not the prettiest, and item 2. And still, we have grouped two values together inside this John data type and inside, this John variable and this Jane variable. Okay, let's take a look at the let's take a look at the types of item 1 and item 2, even though this is not going to be surprising. X is a string, well, it's a nullable string, and Y is a date only. Makes perfect sense. Same applies to Jane. There's no requirement to have them both equal as types, but in this case, for the purpose of this example, I want them equal. So X is also a string, Y is also a date only. Now, one thing that happens is, of course, in C# everything can be combined, so there aren't any features of the language that are sort of shallow bodies of water. Everything is interconnected, and every feature of the language can be used with every other feature of the language. So we could define the those as an array of these two tuples, which happens to be pretty cool if you think about it. Because now, given that the types of these two tuples are created equal, then I can put them in an array. And now the type of those will be an array of tuple of string date only. Of course, you could also have an array. Well, okay, now I'm going to be a bit silly, because this data type doesn't make any sense, and say, okay, the those are an array of tuples where the first element of the tuple is a string and the second element of the tuple is an array of date only. And we can keep composing. We can have an array of tuples, inside arrays, and so on. So you can nest truly as far as you want. Armed with tuples and arrays, you could already arguably define an absurd amount of data structures. So already arrays and tuples are, and lambdas. Then this would actually be the basis for a pretty decent functional programming language already. But so what we're going to do is now we're going to study alternative mechanisms that have various accents and properties that are different from the tuples we've just seen. And then also we will study a way to define types where the fields have names, because now, if we go back to this example, well, okay, so you can see that by inspecting the name and surname, you guess, okay, item 1 is a string, item 2 is a string, and the item 1 is the name, and item 2 is the surname. You kind of guess because you see the example, but sometimes, well, you don't really see how things are constructed. So it would be good to state that the first item is the name and the second item is the name inside the tuple. And yeah, for the compiler, this absolutely doesn't matter, because for the compiler, it just needs to know, do I get the first offset or the second offset? But for us, as humans, that's quite important. So we're going to build up towards that. Do remember that tuples are immutable. So even though these tuples are references, so how is this stored in memory? Well, it is stored in memory as follows. We have, of course, on top of the stack, we have the those, and let's say this is reference 0. And then, well, we also have X, which is John, Y, which is Doe. And then we have the heap, of course, and in the heap, we have at reference 0. We have, well, let me call this just reference 0, it doesn't matter that much. At reference 0, we have an array. The array has length 2, and the elements are, let's say that this is reference, now we will call it reference 1 and reference 2, because I don't want to count the bytes, but actually reference 1 should be replaced for the actual size of the bytes. So reference 1, and reference 1 is now the tuple. So inside here we could say that there's a John and Doe, and inside here we could say there's Jane Doe. Actually, strings are also reference types, so this would look like properly like this. We would have reference 3 and reference 4, John Doe, and then there's reference 5 and reference 6, Jane Doe, and then here we would have the references. So this would be reference 3, this would be a reference 4, this would be a reference 5, and this would be reference 6. And those of you that are the most sharp-eyed will also realize, oh, wait a second, but then you didn't copy X and Y. That is true. You only copied their references. Now, references have this big advantage that indeed they are fast to copy. So if you have a string, and a string might also be like, a gigantic piece of text, could even be megabytes of text. So you don't want to copy the string around. The strings are immutable, so if you have a reference to a string, you are like 100% guaranteed no one will be able to change it under your seat. So you may just use it with certainty that it's going to be stable, it's not going to change. Okay, very good. So references are easy to copy, easy to pass around. And when you make a copy of a reference, it feels like you've made a copy of the original object. And if that object is immutable, like a string, no one can change it. And also, the tuples created with tuple.create are also immutable, so no one can change it. So you can just pass them around by reference. It's completely safe, and the references will not just end up referring to different values because somewhere else in the program someone decided to change them. Okay, but you can see there's also a lot of jumping around, and sometimes this jumping around across memory is not ideal. So if you want to read the surname of the second item of the array, okay, so you have the those, have to look at ref0, okay, first jump, now you're somewhere else in memory because you were on the stack memory and now you're in the heap, okay, no problem, then ref2 jump to ref2, then ref6 jump to ref6, okay? So all of these references might, in some cases, actually have a negative impact on performance. So if you have a lot of these jumps in memory, it might be that your program becomes slower because all these jumps take up space on the cache, basically, because different areas of memory have to be looked at. That's why C# always offers the value. So this is the reference tuple, and C# also offers the value tuple. And the value tuple is very simply just brackets. First of all, it looks awesome, but not only does it look awesome, it is not stored in memory in the same way. Let me change the type back to the one with the birthdays. Now it's going to be very unchill. What was it? 0412. Yeah, not that it matters, obviously. Okay, there we go. So now here we can see that the type is different. It's not a tuple, but it's a string and date between regular brackets. And again, very pretty, but especially these, and of course, these value tuples are accessed exactly in the same way as the reference tuples. So we just have item 1 and item 2. Of course, item 1 is a string. Of course, item 2 is a date only. But the tuples live where you declare them. So there's one reference layer, one level of indirection left. I'm just going to leave those as ref3, 4, and 5, and 6 because the numbers are just identifiers in this. So this means that you actually get copies of the tuples. So if you say those of 0, then John is actually a copy of the tuple. And if the tuples are smaller, like two floating point numbers denoting a 2D point, like 0.5 and minus 0.5, for example, well, actually, I've done plenty of video game development, so passing these little things around is actually faster because these are small things. So value tuples like these ones, when you assign them or pass them as arguments to a function or whatever, you actually make a copy. And if it's small, the copy is fast. And because there are less references, your memory is just less fragmented. And so reading your memory is more of a sequential exercise. I do understand that it will take a bit of a fair bit of experience, performance monitoring, specific requirements of an application, etc., in order to understand which tuple are you supposed to use. But it's good to know that they both exist, and it's good to know that they have a different behavior. Now, let's take a look. Value tuples are mutable. Mutable actually means that we can reassign them. And let's print john.item1, but let's also print those of 0.item1. Let's take a look. Oh, it's yes, that's perhaps too far into the future. I didn't see it. Okay, so we get Johnny and John Doe, meaning that this is interesting. So because and this is the kind of thing that you should be aware of, because they are value types. If you make a copy, well, what happens here? If we've made a copy, so on the stack all of a sudden now there's a new variable which is John, and this variable, it starts as a copy of ref3 and ref4, then all of a sudden we change the string, so this becomes ref7, and ref7 is Johnny. So now, when we say those of 0.item1, that's still those of 0.item1, that's still John, because we made a copy of the tuple. But when we look at John.item1, well, that simply jumps to ref7. Quite an important distinction, this. On the other hand, if we had created this with tuple.create, well, now the tuple is immutable, so this is not allowed. And that's because the people who built C# have a lot of experience, and they discovered that having these shared references, so now these are not copies anymore, so John and those 0 are literally the same, are two different references, so in that sense a copy has happened anyway, but it's a copy of a reference, and because different parts of your program might contain references to those same values, to that same value, and one might change it, but the other doesn't see the doesn't expect the change, and that introduces a logical bug, then these reference tuples are immutable. So mutable references are usually frowned upon. So it's mutable values that you copy around, like integers, value tuples, etc., or immutable references. We will see this pattern quite a lot. It is possible to perform a conversion. So if we have such a tuple, we could say that we want to turn it to the regular tuple. And now we cannot reassign. Now John is a reference. Well, let me delete this. So now John is a reference, and we cannot reassign it anymore because the reference tuples are not mutable. We can also convert again a tuple to a value tuple. Okay, this is quite a silly long path, and now it's mutable again because it's just a value. We could also say, okay, I want to create the tuples originally, and then for this Johnny thing, I want to create the value tuple, modify it, and then, for example, I could say, okay, when I'm done modifying it, I want to put it back. But before putting it back, I have to convert back to the tuple. This could also be a pattern. It's not a crazy one where you have the references. For example, in an array, you make the local copy, you turn the copy into a value tuple, you modify the value tuple. The rest of the program doesn't see this yet because the value tuple is only by definition local to a given context, be it a function, be it a class, so a sort of module of your program. And then when you want to put it back, you convert it to value tuple and you put the reference wherever you want. Value tuples has a very, very nice little extra. We can and will give names to our fields. So now I'm just creating the array as an array where I don't specify the type, I just let C# figure it out. But here, as you know, I can put the type of the array. I could put as type string and date only, and this would have no value whatsoever. But I could say, no, these fields have names. And this field, the first one is full name, and the second field I don't bother to give a name to. But no, of course, I also want the name of the second field. Now, item 1 and also item 2, of course, are still present. But, very exciting, I now have the full name and the birthday available. This is one of those features where I really feel compelled to point out this is only for the human. This is not for the machine. Like, the machine doesn't care that in the source code this thing is labeled full name, or it's labeled birthday, or it's labeled Caroline, you know? The computer just wants to know which bit of memory do I have to access. So for the computer, that full name becomes a given offset in memory. So how many bytes from the start of the data structure should I read? And then obviously the type. The type is very important because it says, and how many bytes do you actually read? But this one is only for us, meaning that a lot of sophistication in programming language design has to do with the human reading and not with the computer executing. Just like we've given names to the fields, sometimes, quite often actually, we want to be able to give a name to our custom types. This happens when those custom types are used in many places, where those custom types are very important for the domain we're modeling, etc. So consider, for example, a program where we manipulate some interrelated data structures, also data structures that need to refer themselves. For example, we could say that we have a user. A user can have one or more active subscriptions. An active subscription has a start and an end time, as well as payment information, and an active subscription refers to a product with a price and payment frequency. So now we have users referring to subscriptions. Subscriptions have payment information. Subscriptions also refer to a product, a price, a payment frequency. So we are probably going to define these types and use them as parameters to functions, as components to tuples, elements of arrays, etc. So we really need to give a name to these things because, well, this name will be used to denote these structures across, well, actually the whole program. So the simplest data type that C# offers with a name is the record. A record looks a lot like a tuple with a name. That's as simple as that. One of these value tuples with named fields and a name. Now, let me show you how this works. We start with the keyword record, then the name of the record, and then between brackets, the value tuple equivalent. So for example, string name, well, let's say we have the user, we have the name, the surname, and, well, as we promised, the active subscriptions, which will be a subscription array, active subscriptions. Okay, of course, subscription doesn't work because we said that's another data type. The subscription, it has a start and an end time. So date time start, date time end, as well as payment information. Well, actually, in this case, I will just call it payment information. This pattern, where the type and the field are the same, it happens more commonly than you might imagine. So payment information, this will be, okay, it will be, let's say we have an enumeration, payment type, which would be credit card, cash, or PayPal. And then here we would have the payment type plus some extra data that I'm not going to model because we're not going to model a full payment information. Why is it not happy now? Oh, this is quite silly. Because I'm using this new C# structure where a source file can just contain statements without defining classes, etc. If I want to have declarations, they have to be after the first statement. Yes, otherwise you have to use the old style static class program, which I'm not going to show because it's really boring. Okay, anyway, I'm not going to model the rest of the payment information that comes with polymorphism later. And so actually, you know what? We're just going to remove the payment information and just model it like this. And obviously, you can imagine we could continue. We could have products, and the subscription might actually refer to a product that you subscribe to. Imagine that these products are, I don't know, online videos, courses, services, whatever. And yeah, this continues. It's funny because this part of the program is what I like to refer to as a taxonomy. So we model what exists in our program, the structures that exist. We're not defining how many users, how many subscriptions, etc. Not at all. But what we are doing is we are defining what is possible in our program, but what is and what is also impossible. What our program is incapable of modeling. The data that doesn't fit the taxonomy cannot be modeled, and this isn't negative. It's actually, whenever you define structures like data structures, what you choose not to model with your data structures is as important as what you choose to model, of course, because what you choose not to model defines focus, and what you choose to actually model defines possibility. And so creativity happens at the edge between focus and possibility. You cannot model the single atoms and molecules of everything, of every data structure that you want to have. Like, instead of having a user, you have an array of molecules, that wouldn't make any sense. That would be unfocused. That would be way too much information. And yeah, at the same time, you do need the name and the surname and the subscription, so that needs to be there. So now, at this point, this user can be employed wherever we want as a declaration. So I could say that I have a new user array. Well, of course, this doesn't work because I need to instantiate users now inside the array. How are these users instantiated? Well, we have again the new keyword and the type that we want to instantiate in between brackets, and you see the IntelliSense is doing a very good job at suggesting what's supposed to happen. Now we can put John Doe, and then, well, and then the active subscriptions. Oh, and you know what? I'm not going to put any subscriptions here, just, to save a little bit of time. Then we can also create the second user, which is again Jane Doe. And well, let's say that Jane actually has a subscription. So Jane has a subscription. And let's instantiate the subscription. Subscription starts today, and today plus time span from days, so 30 days from today, and the payment type will be by cash. So Jane will actually bring the cash. Okay, now do we have item 1? Now we don't have item 1 anymore. Now we have the name. Records are also immutable, so this cannot be done. We cannot reassign the name, but we can of course read the name. So records are again reference types, and by now you know exactly what this means. We can also go and get Jane's first active subscription and show the payment type of this active subscription. So this program is not very exciting, but well, let's, the payment type, which is cash. So we see John Doe and cash on the console. Okay, very good. And thanks to this immutability, well, most of this data structure, with the exception of the array is mutable, so the array can be changed, but all of those structure cannot be changed and is based on references. Obviously, again, we can compose things. We can see here an example of composition. Sometimes one might simply want to, well, group two people very quickly, and then say var users would be, and then you can still use those simpler little tuples. for small temporary stuff, and this will be a value tuple of user and user. Usually we use tuples for things that are temporary and that as such are types that are not going to be reused multiple times, so you want to quickly put your things together and be done with it, and it's clear what those things are by the type without looking at the name of the field, and wherever you need a richer structure, you do use records. We could see, we could, for example, check whether or not a user has an active subscription. Well, actually, let's say that these are not the active subscriptions, but just the subscriptions, and we want to know if there is a subscription that is actual, or that is or that is active. And a subscription is active if the current moment, if datetime.now is between the start and the end of any subscription. And this is something that's quite useful to have, but it's not a value, it's a property. It's something that we would calculate from the user. So I'm going to say that there's a public, so something that can be called from outside the definition of the user, because these curly brackets, they also define a scope, and within this scope we can touch anything that has been defined in this very same scope. But if you also want others, so outside these curly brackets, to be able to use whatever I'm about to define, then I have to mark it as public. And let's say that we want to know if the user has active subscriptions. Then there's a little arrow which is equal and greater than, but thanks to the font I'm using, then they become a neat little arrow when I put them next to each other. And then I can say, okay, has active subscriptions. Well, I have this. And what is this? Well, this is literally a reference to the user we have called has active subscriptions upon. So if we call it on those of 0, then this will be the same reference as those of 0. If we do those of 0 or those of 1 dot has active subscriptions, then this will be those of 1. We will see it with the debugger in a moment. Then we take the subscriptions. We can say, well, if there's any subscription, now any is a function that takes as input an extra function, so n is a higher order function that for each subscription returns Boolean. And this whole any determines if any element of the sequence satisfies this condition. So we take the subscription and we check if datetime dot now is greater or equal than subscription dot start, and datetime dot now is smaller or equal than s dot end. There you go. Sometimes I don't even bother to give a proper name to this, so these lambdas in my code occasionally might even have as parameter name underscore, which is actually kind of okay. Now let's see. Does John have an active subscription, and does Jane have an active subscription? Let's take a look. Now notice that has active subscriptions is just a Boolean. It behaves almost as if it were just any other regular field, but this is a property, and properties are computed fields. They can be computed simply, or they can be computed in a complex way. Let's run the debugger. And okay, let's take a look. We have the those. Yeah, this is the whole memory. I actually like this very much. Beautiful, but utterly unreadable. And you can see all the values that are contained here, all the characters. Yes. Anyway, so we have the those, and the those are these two users. marked as 0 and 1. Okay, very good. Let's take a step. Oh, sorry, that's, yeah, okay, we have a second chance. We get false because of course there are no subscriptions, so there are also no active subscriptions. Let's step inside. Oh, this didn't really do what I was hoping it would do. Let's move the breakpoint here and hope the thing behaves well. Okay, yes. Now, we are now running the first instance of has active subscriptions. But obviously inside the definition of user and its body, this is the body of the type of the record, there is no reference to those John and Jane. So this is generic, this is for all users. But which of the many users across the whole lifetime of the application are we talking about? Well, that would be this, and in this case, this is John Doe. Now, this changes because we're entering in the second invocation evaluation of has active subscription, and so this now happens to be Jane Doe. Also notice that has active subscriptions has its own stack frame. Why? Because it is a function. It is a function that has no parameters, and as such we call it just by reading the value almost as if it were a value. This is very nice, it's very pretty, but make no mistake, there are two stack frames, main and actually, yeah, there's three stack frames now because we're inside any at this point. Very nice. Yeah, and you can actually see these stack frames, and you can see that the variable this only exists in here inside has active subscriptions. We could also create a neat utility. Let's see this once again. We could say, okay, but what if we want to store the name and surname, which is good because they are separate, but I also want to have the full name. Okay, so name and surname, there you go. And now I could print the full name, which is a useful shortcut, you know, to not have to retype name plus surname every time. So these properties actually make a very big difference because they allow you to define, let's say, the basic properties, the basic, I should probably say fields. So these are the fields, like the variables and values that are grouped together in this record. That's sort of your base. But then you can compute whatever you want on top of them, and here you have the things that you actually use. It wouldn't also be crazy to imagine that you use these properties as much, if not more, than the fields. But sometimes you just need to have the original fields. So yeah, that's it. Sometimes though, we need more than just properties. So for example, because we actually need to compute something that depends on some extra parameters. And in this case, we can define full-blown functions, and when these functions happen inside a custom data type like a record, we call them methods, because unlike functions, they also have this implicit this parameter. So, for example, let's say that I want to know if a user will have an active subscription in a series of days. So I want to know, will we have an active subscription? Oh, by the way, I can put the curly brackets here and then declare all the variables I want. I do really like the arrow syntax, but yeah, it doesn't matter that much. So now I can actually say that a user will have an active subscription if now plus time span from days is greater or equal than start, and now plus days is smaller or equal than end. Now here you might argue perhaps it is a good idea to actually define the moment, var tested moment, as a variable. Because these big repeated expressions, well, they are quite bad for the maintenance of your code. And there you go. Now you could argue that has active subscriptions is simply this dot will have active subscription in 0 days. So now it's good to reuse logic when it's very similar. And so basically has active subscriptions sort of defaults the parameter of will have active subscription in to a value of 0. And now the question is, will Jane have an active subscription within 20 days? Let's test this. The answer is true. Will she have it in 100 days? And the answer is false. Will she have it in 31 days? Because her subscription lasts from today to today plus 30, and that is also false. Now that we've seen the basics of records, it's time to ask one fundamental question. That is, like we've always asked, how does this feature of the language, records, integrate into the remaining features of the programming language? In particular, we have seen tuples, and it does stand to reason that it should be possible to perform automatic conversions or so-called destructurings or deconstructions from records to tuples that obviously have the same structure, so the same fields with the same type in the same order. So we have John here, and this John variable has type user. We could say that, well, this is a signature, a type, and the variables at the same time. So we could say that this is equal to John, and look what happens. Yeah, the thing actually just works out of the box. Let's unpack this. So here the name is now a local variable. Let's call it John's name, and the surname is also a local variable that has been introduced, and these are the John's subscriptions. And now, well, John's name is just a full-blown variable. We don't even need to put the types here. We could just put var, and this would also work, because obviously it's clear that, well, if John is deconstructed into a tuple with 3 elements, the first variable is going to be a string, and, well, there we go, the second is also going to be a string, and the third is going to be an array of subscriptions. This sort of assignment actually is a big deal, because suppose that you have a function somewhere that expects a tuple with name, surname, and subscriptions. And yes, you have declared your user record, and it's nice to give a name to things, etc. But somewhere else you might simply have a generic module that doesn't really care about your user data type, just cares about the data contained into it. By letting the language perform the mapping for us, we are freed from having to think about these trivialities, because otherwise, yes, of course, you could do this manually by stating, okay, John's name is equal to John.name, and John's surname is equal to John.surname, and so on. But by letting the language just take care of this trivial conversion, because there isn't really any value to this from a business logic perspective, this is not really adding any features to the program, any algorithm, anything, then, well, we are freed from doing this, and we can focus on the things that actually matter. Now, but sometimes we might want to define custom ways to convert a record into a tuple. For example, our user might be used in a context where only the name and the surname are expected, and, well, not the subscriptions. We've seen that we can add methods, but if we add one special method, which is called deconstruct, public void deconstruct with a series of out parameters, then we can dictate how those parameters are assigned when deconstructing into a tuple. The parameters are marked with a special keyword that we haven't seen yet, the out keyword. So I could say out string name, out string surname. Out means that even though usually when you pass an argument to a function, the argument is simply copied. So you can't reassign the thing that was passed. By saying out, we're actually we're actually requesting the language that if someone assigns a name here inside the construct, they're not reassigning the copy that was pushed on the stack, but they're reassigning the original. So an extra layer of referencing is introduced here. What we can do is simply say name is equal to this.name and surname is equal to this.surname, and well, the deconstruct method is now happy. And what we can do is, of course, we can use this standardized deconstruction that maps every field to every corresponding field of the tuple on the left hand side. But we could also say, there you go, that if we try to assign something which doesn't have all the fields, obviously C# is not going to decide for us which fields to discard. But well, in doing this, we are providing our own definition of how to discard. In our case, the subscriptions. Now, armed with this deconstruct method, it is possible to perform some pretty advanced operations from within a switch statement. So let's say we want to define a function that checks whether or not a given person is called either John or Jane. We will be able to do this implicitly by using our deconstruct method. Look at this. So let's have a function, bool, that says whether or not it's John or Jane. Is John or Jane though? Then, well, of course, we take as input a user. Let's just call it you, not very exciting. And now what we return as the boolean is a switch expression. So we take the user and, we take the user u and we switch over it. And in here we can put the patterns of a switch. So let's start with the default case, the one that's always going to match in case no other pattern matches. And before this, obviously, we want to put the specific cases, the specific patterns before the fallback scenario. Say, in case of name and surname, well, of course, this is always going to match. And then here we can say the name is John, or the name is Jane, and of course, the surname is Doe. Then we separate the patterns, and we separate the patterns with a comma. This is already pretty cute. So we could say, we can call this is John or Jane Doe, and pass John to it. And if we run this, well, of course, it shows true as a result. And if we rename this to Johnny, let's run this again. And of course now it prints false. But first of all, let's see what happens here. When we perform a switch operation like this, then what we're saying is that these variables have to come from the deconstruct method. So this is doing quite a lot actually already. So this is calling deconstruct, introducing the variables, etc. I don't think we even need this, to be honest. Yes, we don't. But the pattern can also, so this pattern here that we get from deconstruct, may also contain the values we want to match against, so that we get rid of this ugly expression. Well, we do want to match against the Doe anyway, so let's already say that we don't really care about the variable surname to be introduced and to be checked. We just want the result of the check. And the name, well, we can say, okay, if this is John Doe, when we get true. If this is Jane Doe, then we get true, and otherwise we get false. It's actually pretty exciting. So what we're saying is call deconstruct. If deconstruct is available with two strings, then get those strings, compare with the values in here, and, well, if the values match, then do whatever is available here. You could also say that we want this to be to also have subscriptions. So you could say, okay, now we want to have a var subscriptions, and because there is a standard deconstruct method with three variables, with three fields, well, this is going to use the standard deconstruct method, and then we could say, well, we also don't really care about people who don't have subscriptions, so the length of the subscription has to be strictly greater than 0. And let's also do it on the second one. And now what we're doing is, okay, is saying, call deconstruct, get all the fields, and call the deconstruct as three fields. The first two we don't want to map to bind to variables, we just want to compare to the values Jane and Doe. If the comparison to the values is successful, then also extract the subscriptions and evaluate whatever is to the right of the arrow. And this is brilliant, because it's saving us from all of this boring, crappy extraction of variables and calling the right deconstruct method. The language is taking care of the structure for us, and what we do is we perform comparison, we perform the decisions, we define the business logic, but we don't really care about these minor structural details. Alright. And, well, of course, we could also say that there is a special user who is someone very rich, and, well, we always let them pass the test because they are a big donor. So, I don't know, George Rockefeller. Yes, there you go. And then in this case, you can see that we're using the two deconstruct methods, one after the other, implicitly. We conclude our discussion on records with the keyword. Records are immutable. This means that even though they are reference types, so we just refer to them, we can share the references safely between modules of a program, because once a record is created, there is no way that any component of our application may change it unexpectedly from under our feet. But what if we want to modify a record? Well, the only way to do this is to create a new record where we copy the fields that are unchanged and where we keep the fields that are supposed to change. Now, if there are many fields in the record, but only one has changed, this could be very tedious if we had to do this by hand, not to mention also error-prone. But fortunately, there is a special keyword called with that was introduced precisely for records. So let's say that we have this John record and we want to modify it. We want to, I don't know, change the surname. Now, and let's say actually that we want to change the surname that goes into the John record, not the one in the original array. So how do we do this? Well, we take the reference to the record that we want to, well, not really modify, but actually recreate, changed. Then we say with, and then with between curly brackets, the new value of the fields we want to override inside John. So we could say with name equal to, well, let's put this back to John because we had changed it to Johnny. Now, let's let's clean up a little bit of our previous attempts. And if we write those of 0 dot name, this will be unchanged. This will still be Johnny. On the other hand, John dot name being a copy that has been overridden, it has gone to John. Other values, such as the surname or the subscriptions, will remain exactly the same, because it's a copy. What this looks like in memory, and I think it's always interesting to ask ourselves the question, okay, well, what is the memory layout of this thing? Well, on the stack, on top of the stack, we have those. This is some reference. Let's say it's a reference 0. Then we have John, which is, let's say, reference 1. I'm not really putting them in order of creation, so the indices 0, 1 are not chronological. Chronological would be even something else. And Jane is a reference 2. But let's be careful. In the heap, at a reference 0, well, we have an array. I'm going to simply say we have this array, and it contains a reference 3, because the original Johnny Doe has been copied, so it's not ref1, it's not the same as John, and ref2, that would be Jane. And then we have ref1. Ref1 contains, I'm just going to put it down as a tuple. It's John and Doe. So ref1 is the copy that has been made into the John variable, and the subscriptions. Then we have the reference 2, which is Jane Doe, and the reference 3, which is pointed at by the first element of the array. This is Johnny Doe. The interesting thing about the with keyword is that it's really meant to make a copy of an immutable object, because if the object is immutable, then making a copy of it is of paramount importance, of course, without having to write down all the fields that stay the same. Because of course we could have said, no, let's simply make the copy manually. Let's create a new user where, well, we take those of 0 dot name, those of 0 dot surname, and of course those of 0 dot subscriptions. This is error prone again, and not to mention like terribly boring. You just don't want to be caught typing this, but you can also make mistakes like this. Well, in the case of name and surname, it's quite trivial, so one tends to put the name before the surname. But what if someone made a change to the underlying definition? Yeah, then this can be broken pretty easily. Another thing that is worthy of mentioning is that, well, the with keyword also does come from the wonderful little world of functional programming. The ML family of languages, ML, OCaml, F#, were languages where the with keyword and records were experimented with in the first place. Well, no, not entirely in the first place, but they were made reasonably popular. And it's interesting to see now C# picking this up almost one-on-one. One note, though, is that here we're mixing mutability and immutability, and this can lead to very interesting patterns. So the records themselves are immutable, but for example, the array of subscriptions isn't, because, well, it's an array. No one stops us from mutating the record, because we could say, oh, well, no, this is an empty array, but those 1.subscriptions of 0, and this could be made into a new subscription where we put whatever we want. Let me just copy this. I know this is and let's say that this is made by credit card. So by mixing mutability and immutability is a bit of a dangerous thing, I believe. So one should take care of trying to have either an immutable design pattern that is dominant in the application, or if you really need to, mutable, but having them both, that's not ideal. So we will see later on how to use libraries that behave like arrays, but in an immutable way, the immutable collection library. Now, Reference types like arrays, when we try to compare them with the double equal operator, can actually be quite misleading. Let me give you a very quick example. Let's say that I create an array of integers 0, 1, and 2. And I compare it to an array 0, 1, and 2. Let's run this. Let's see what happens. This gives false. That's quite embarrassing because the double equal operator, the equals operator, just well, by default on types such as arrays, so on reference types, compares the references. And because these are two arrays that are created, even though the values are exactly the same, the references in memory where these arrays are placed are different. And so the result that we get is not a value equality, but a reference equality. It is possible also when defining custom data types to override, to redefine the comparison operator. But on records, this is already done for us. So records, well, let me compare, for example, these now two new subscriptions. And let's see what happens now. We get true as a result, because records compare the fields one by one and determine whether or not the fields are the same. Now this is very, very handy because record equality can be relied upon, and because we're also sort of psychologically wired to say that if you compare one with one, you don't want to think about where these things are in memory. But it's also one of the reasons why I'm hammering on references and the state of memory, because the state of memory, the shape, the layout of memory, and what is the same reference of what, is very important because it determines, for example, the result of the equality operator. And there are many things that can be said about whether or not thinking about memory is useful. And you can see that with the records, the language designers are moving us away from this model of memory, but it's still there, and it's very prominent in many cases, so we have to think about it. Now, let's also compare the same user. And now we get false again, and well, why is it false? Because the comparison of the first two fields, because obviously this record value equality compares the fields one by one with their own out-of-the-box equality operator. The first two compare and are the same, but the last one is an array, and unfortunately the comparison of arrays in this case breaks our normal, expected, breaks our expected neat value equality. So yeah, something to keep in mind. Now, this concludes our discussion on custom types and records. Armed with knowledge of records, functions, lambdas, arrays, and tuples, you are already in state of building a lot of programs in C#. This is the, let's say, beating heart or the most productive code of the language. And in the next lessons, we're actually going to dive into more advanced features, which are all about the modular organization of code. So, well, things that are always less required, you could say, in order to be able to express thoughts on business logic, and more oriented towards the human who needs to make sense of their code. As always, thank you very much for being here. Thank you very much for listening. The best of luck with your studies, and until next time, bye bye.